Hi, well, we're looking at beams and specifically at the moment the internal forces in beams caused by flexure or bending. And so we're kind of starting off with a bit of a review, kind of going back to the statics of circumstance, but we're going to build up this simple problem and step it through in successive iterations to look at some of the tools that we use when we're looking at bending. So the first thing we have to do is, of course, determine the reactions. I'm going to go through it fairly quick. Like I say, this is a bit of a review. And before we can do the reactions, of course, we have to do the free body diagram. So I've dropped my geometry down. I've got my center line in for the free body diagram. I've labeled it. And now it's just a matter of putting on my external forces. Okay, so working left to right, we have, of course, reaction forces at A. We have a vertical and a horizontal. And we have a vertical reaction force at the roller at B. And so we can label those reaction A X direction, reaction A Y direction, reaction B Y direction. I should put in my x-axis here as that's important, although it is in the original drawing. And then we have our externally applied force of 200 kilonewtons at the 1 meter mark. And what the problem is asking us to do is to look at the internal shear force, denoted by V, and the bending moment, denoted by M, in the beam at two different spots, one at x equals 0.75 meters and one at x equals 1.75 meters, really looking at either side of the point load so that we can get that. So let's get on about doing the reaction so we can jump in here. So I'm going to start by doing sum of the moments about A is equal to 0. I'm going to set my clockwise as positive. And so working across the beam, I see that's got my 200 kilonewtons and a moment arm of 1 meter. And that's trying to turn it clockwise about A, so it's positive. And then the reaction at BY is trying to turn it counterclockwise with a moment arm of 3 meters from A. So we're able to solve RBY is equal to 66.7 kilonewtons. So go right on. I'm going to do sum of the forces in the y direction is equal to 0. And that's equal to my RAY minus the 200 kilonewtons plus RBY, which we already know is 66.7 kilonewtons. And so we're able to solve for RAY, and that's equal to 133.3 kilonewtons. And I'm just going to transfer those over to my free body diagram. So RAY equal to 133.3 kilonewtons and RBY 66.7 kilonewtons, and we know Rax is equal to 0. Some of the forces in the x direction is equal to 0. There's no other forces in the x direction, so you could certainly write that out and add that to the problem solution. So right away, we want to go on and look at our internal forces. So internal forces, and we're going to start at x equals 0.75 meters. And to do this, what I want to do is to get in the habit of drawing a partial free body diagram. So I'm just going to set it up down here, and like the free body diagram, add reactions, applied forces, and internal forces. And so what we have is we have our 133.3 kilonewtons acting at A. This is some distance x equals 0.75 meters, and there's no other externally applied forces on that section. They all happen after that. Remember, this is the method of section, so you're throwing away everything, one side or the other of the section. But what we need to do is we need to add our internal forces. And so we're going to show the shear force, V at x, and our bending moment. I'm going to draw them in accordance with our sign convention as positive. And that way, if we determine that they're positive, they will have a positive number in our calculations. So I'm happy with the partial free body diagram. So now all I need to do is to apply statics in order to resolve them. So I'm just going to get right at it. So sum of the forces in the y direction is equal to 0. We have our 133.3 kilonewtons acting up, and we have v at x acting down. And so we can solve for v at x and figure out that it's equal to 133.3 kilonewtons, which is one of partial answer to one of the first question. And then to finish that off, then we'll do some of the moments, and we can choose where to do our moments about. In this case, I'm going to choose the moments about x is equal to 0. Again, I will use clockwise as positive. And so for about x, we have the 133.3 kilonewtons multiplied by a moment arm of 0.75 meters. And the v at x is not, it has a 0 perpendicular distance to that position, so it disappears. And then we have m at x trying to turn it counterclockwise, so it gets a negative sign and goes in there. And we can isolate for m at x and solve for it to be 99.975 kilonewton meters. And so those are the internal forces at x equals 0.75 meters. So being somewhat repetitive, what we're going to do now is we're going to do x equals 1.75 meters, and we're going to do exactly the same thing. Go down here, say at x equals 1.75 meters, and we need to draw our partial free body diagram. So I'm going to put it in here, add our forces, and our internal forces. And we'll do our labels. So our V at x, our M at x, our 200 kilonewtons, and our 133.3 kilonewtons. So partial free body diagram is a little bit more complicated because we now have the 200 kilonewtons off to the left-hand side. Of course, we could have chosen to do it from the right-hand side, in which case we would have only had RBY. It might have been a little bit simpler, but let's keep with this. So we're going to solve for our internal forces by doing some of the forces in the y direction is equal to 0. So we have 133.3 kilonewtons acting up minus 200 kilonewtons acting down minus v at x acting down. So we isolate for v at x and solve to get a negative 66.7 kilonewtons. So that's great. We just need the m at x. We're going to solve for it the same way as we did above. So sum of the moments about x is equal to 0. We're going to do clockwise as positive. And so moments about x, we have our 133.3 kilonewtons multiplied by its moment arm, which is 1.75 meters, minus 200 kilonewtons multiplied by its distance, which is the 1.75 minus 1, so 0.75 meters, minus m at x. So we're able to isolate for m at x, and it is equal to 83.275 kilonewton meters. So we'll just underline those. So we have our shear force and bending moment forces solved for our two locations as asked for in the problem. This is just a simple reminder. So back to statics. Now what we're going to do is we're going to go on, same problem, and we're going to look at graphing our internal forces across the entire length of the beam so that we know what the shear force and bending moments are internal to the beam, axial force if necessary, across the entire length, and we can analyze it and figure out what to do with the beam from there. So this is just setting the stage, and we're ready to go. So we'll be back with the next video, and we'll look at the shear force and bending moment diagrams for the beam.